Okay, so today we are talking about electron configurations and valence bond theory just real quickly. If you have a periodic table handy, you want to pull that out. Actually, you know what? I'm going to give you a blank one because that will probably be better. I don't have any full page ones. These little mini ones will do the job. You're probably going to want to write on your periodic table today. Pocket size version. You never know when you're going to need a periodic table in your wallet, right? Keep it in your pocket for when you're out with your friends. Okay, so last time we talked about the quantum model, right? We said that every electron, or the general location of every electron, is defined by 4 quantum numbers, right? N, L, M sub L, and M sub S, right? We said that location, the general location of every electron, is designated by an orbital, which is defined by those 4 quantum numbers. Now, the Pauli exclusion principle says no 2 electrons inside a single atom can have the same 4 quantum numbers. Because if you're thinking of quantum numbers as like coordinates, you know, quote unquote coordinates, to that electron's general location, obviously no 2 electrons have the exact same 4 numbers. Just like if we're thinking about your position on the planet right now, right? You would first start by stating what continent you're on, then what country you're in, then what state you're in, then what, I don't know, county you're in, then what building you're in, then what room you're in, and then which seat number you're in, right? Seat number 1, 2, 3, 4, seat number 1, 2, 3, 4, 5, right? Each one of us will have a lot of numbers in common, like continent, country, state, county, building, room, right? But we're each going to have unique aspects of our location too. So no 2 electrons are going to have the exact same 4 quantum numbers. They might have a lot of things in common, but they obviously can't have the exact same coordinates. So when you talk about you know, things beyond hydrogen, things get messy, right? Especially if you're thinking about, I don't know, chromium with its 24 electrons, or you know, anything beyond 2 electrons, right? Things get messy because you've got a lot of electrons to take into consideration. So we write electron configurations. That's the reason why we write electron configurations. You could think of electron configurations as like a list of directions to the position, or the general position, of all the electrons in an atom, okay? Electron configurations, you could think of them as like a list of coordinates to get to all your electrons, right? Because we need to define the location of all of our electrons, right? There are going to be a lot of things in common because they're all in the same atom, but there's some of them will be in s orbitals, some of them will be in p orbitals, some of them will be in d orbitals, right? So electron configurations are a list of the coordinates for every single one of the electrons in your atom, so that each electron has its defined space and we're not violating the Pauli exclusion principle. So here are the rules. We're going to look up how many electrons are in your atom. Easy enough, just look at the periodic table. Now, of course, if it's an ion, right, we would add electrons for an anion. We would subtract electrons for a cation, right? So for instance, if we were doing sulfide, we would add 2 electrons because sulfide has a -2 charge. If we're doing sodium ion, we'd subtract 1, right, because it's lost an electron. So look up how many electrons are in your atom, and then add or subtract if it's a cation or an anion, right? And now your electron configuration needs to represent all those electrons. Every single one of them needs to be your representation. And there's a bullet point with a period at the end of a sentence. That's just funny. Not sure how that got in there. Those are your only 2 rules. So there are 2 methods for writing electron configurations. I don't care which method you use, whichever one makes you happy. So I'm going to show you both. And I'm actually going to just have the blank screen here. So method number one is called a diagonal rule. This is actually the method I learned when I was in high school, way back when. And I hated it. I hated memorizing how to draw the darn thing. if you like it, great. If this is something that works for you, awesome. Okay, a lot of people who are really visual, if you're a visual type person, you'll like the diagonal rule. So just because I don't like it doesn't mean you might not. That's why I still teach it. Okay, because even though it's not my preference, it might be yours. And if it does your preference, great. Forget what I think about it, right? As long as it works for you. So I am going to show you how to draw it. Okay, you need to learn how to draw this thing if you want to use it. It'll be a good test of how straight your lines are. So everybody draw 1 through 8, just, you know, on the rows of your paper. 1, 2, 3, 4, 5, 6, 7, 8. Okay? Now pinch in and pinch in and give yourself some space. But on the same row, 2, 3, 4, 5, 6, 7, right? So we've lopped off 8, we've lopped off 1. Now we're going to lop off again. We're going to lop 2 and 7 off, but we're going to stay in that same row. So we're going to do 3, 4, 5, and 6. So you can tell how straight my scales are here. Trying to make it straight. And then we're going to lop off again, but staying in the same row. Just do 4 and 5. Okay, give everybody in the first column S's. Give everybody in the second column P's. Give everybody in the third column D's. Give everybody in the last column F's. Now we need little numbers. Give everybody in the S's a superscript of 2. Give everybody in the P column a superscript of 6. Give everybody in the D's a 10. And give all the F's 14s. Now comes the test of how straight did you draw. This is always the moment of truth for me. So I'm actually going to erase this at the top so I have more room. Okay, so here's where we start. Start here. Okay, so we're going to start with 1, and then you go down, and then over, and then down, and then it would loop back up and go down, and then it would loop back up and go down, and then it would loop back up and go down, and then it loops back up and go down, and then loops back up and goes down. Okay? Now notice we've invented a row. There's no 8s orbitals. We just put this there so it's nice and symmetric. Okay? 8s does not exist. But we're putting it there so that we've got a nice triangle. Okay? So just keep in mind, 8s is not real. Okay? There's no such thing as 8s. But we put it there just as like a space holder so that there's not just an empty spot there. Now let's do an example. How would we do this? Let's do something not too bad. Let's do aluminum. Okay, aluminum has how many electrons? How many electrons in aluminum? 13. So all my little superscripts need to add up to 13. So we start here at the top. All right, 1s2. Well, 2 is not 13. I got to keep going. So I go down. 2s2. 2 plus 2 is 4. That's not 13, so I got to keep going. 2p. Okay, if I put 2p6, that would get me to 14. Right? Wait, no, that get me to 14. Or 12. Wait, 12. 2, yeah, that get me to 10. Sorry. It's 7:45 for me too. Right? 2p6, that gets me to 10. Now we go down 3s2. That gets me to 12. Now if I put 3p6 here, that would not be good, right? I would have exceeded my number. So This 6 is just the maximum number. Okay, so I can have any number 1 through 6 here. 6 is just the max. So what number needs to go here? I'm at 10, 12, so what's this one? Oh, sorry, 3P1. Right. It's 7:45 for everybody. Does everyone see how we do this? We just start at the beginning and then keep going until all of our superscripts add up to the number of electrons in your atom. So this is how you do it using the diagonal rule. Okay, you just start at the top and you flow down, and like I said, it loops back around and down, loops back around, down, loops back around. So don't forget to loop. Okay, you're looping every time. So why don't you take a second just on your own and you do, let's do a couple. Let's do the ion too, just for fun. Let's do chlorine, and let's do Na+, and let's do sulfide. I'm going to pause the video while you do that. All right, let's resume. So we're doing chlorine, sodium ion, and sulfide. So chlorine has how many electrons? 17. So here we go. We're going to start at the top. 1s2, 2s2, 2p6. That gets me to 10. 3s2. That gets me to 12. 3p6. What does that get me to? Is that what I want? Does this need to be 6? What should it be? 5, right. Make sure that you know that you're not required to fill it, okay? That's just the max number. I have students who'll just fill it just with the numbers on the page because they see the number on the page, they go, oh, that's the number that has to go here, right? You can put any number up to the max. Let's do Na+. How many electrons are in Na+? Sodium's got 11, right? So how many would be in Na+? 10, right? Because if it's a cation, it's lost an electron. So 1s2, 2s2, 2p6. Do we agree? And sulfide, what's the charge on sulfide? It's S. With what charge? -2. So how many electrons are in sulfide? Sulfur has 16. So how many would sulfide have? If sulfur has 16, how many would sulfide have? 18. So here we go. 1s2, 2s2, 2p6, 3s2, 3p6. Do we agree? Do we see how to do this using the diagonal rule? So that's method number 1. If you like the method number 1, great, awesome, use it, okay? Just remember how to draw it. Okay, that's the downside. You need to remember how to draw it. I'm not going to give that to you. Just remember how to draw it. If you want to use the diagonal rule, just make yourself some columns and fill it in. All right, so that's diagonal rule. Like I said, that was the method I learned when I was in high school. And then I learned method number 2 in college. Right, so there's diagonal rule. So there's sodium, right? Just reading off the list. Remember that this number is not mandatory. That's just the max. Now let's do the periodic table method. So label your periodic table to match mine. Now, obviously, this is a really old version of the periodic table because I still have 12 through 18 in here not named. Bad, Dr. Brooke. I need to update my file, right? Because 12 through 18 are all named. All right, label your periodic table that I gave you accordingly. We're going to imagine helium sitting right here next to hydrogen. Okay, so just imagine helium sitting right here next to hydrogen. Draw a box around group 1 and group 2, including helium, and those are all the S block. S block. Now label boron through neon all the way down. Don't include the lanthanide and actinides, okay, so end it right here. Boron all the way down to 113, neon all the way down to 118. That whole group is called the P block. Now remember, we're imagining helium sitting over here next to hydrogen. So helium is not part of the P block, it's part of the S block. Okay, that's the P block. The transition metals, that's the group in between, that's all the rows in between. That's the D block. D block is the transition metals. So 21 through 30. Now, here's where things get fun. We imagine these guys, right, 57 through 71 and 89 through 103, we imagine them shoved in right here. Well, they're actually their own block. They're called the F block. Okay, so the lanthanides and actinides are not part of the D block. They are actually their own block. They're called the F block. This is the method I prefer because you don't have to draw out a diagonal rule. Because now we just read off the periodic table. So whatever row you're in, whatever period you're in, this is the value of n, right? So if this is group, period 1, 2, 3, 4, 5, 6, 7. Notice I said there's no such thing as an 8 because there are not 8 periods in the periodic table. So the value of n here for this guy, this row is all 1. Value of n for all these would be 2. Value of n would be 3, 4, 5, 6, 7. Now there is an anomaly that occurs in the D block. We'll talk about it in a second. So this one comes from your textbook. So now we're just going to read off the periodic table. So let's do sodium. Sodium's right here. So we're going to start at hydrogen, and we're just going to keep going until we get to sodium. Okay, so here we go. If we do, starting here at sodium, we're in period 1, S1, 1S2, right? So that gets us to helium, but we've got to go all the way to sodium. So now we got to go on. Now we're in period 2, so the value of n is 2. 2S12, that gets me to lithium, or excuse me, beryllium, but I got to get going until I get to sodium. So now I'm in 2P, 1, 2, 3, 4, 5, 6. That knocks out everything up to neon, but I'm not to sodium yet. I got to go into the next period, so that'd be 3. I'm in the S, element number 1. So you're literally just reading straight off the periodic table. Okay, the value of n comes from what period you're in. So 1, 2, 3, 4, 5, 6, 7. Okay, so you're just reading off the periodic table until you get to the element you're interested in. Does this make sense? This is the method I prefer because I don't have to draw up the diagonal rule. I can just look at the periodic table. However, if you like the diagonal rule, if that makes more sense to you and it gives you the correct answer, then by all means use it. Okay? Use it, use it, use it. Now, if you're doing an ion, for instance, if you're doing phosphide, P minus 3, right? It's gain 3 of electrons, right? So you would imagine it as 1, 2, 3. It'd be the same as argon. Okay? If you're doing an ion, right? You would imagine you're doing it all the way up to here because it's gained 3 electrons. If you're doing magnesium ion, right, it's lost 1, 2, so you would stop here. Okay, so you just have to count backwards or count forwards based on the number of electrons it's gained or lost. Does that make sense? Now, here's something that happens in the D block. When you hit the D block, the value of n goes down by 1. Okay, the value of n goes down by 1. I still have my diagonal rule. Oh, I don't. You notice you're going along, the value of N is everything the same going across, but when you go 4s, when you hit the D block, it goes down by a row. Okay, so for instance, if we were doing GE, germanium, here's the electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p2. It goes down by 1 during the D block. The answer to it is a complicated quantum mechanical one, so we're not going to get into it. Just remember, think of it as like a tax or a cover charge or some sort of fee you have to pay to go into the D block. And then once you come back out of the D block, you're back to whatever your value of N is from the row. Okay, just think of it that way. We don't need to get into the why. It's a nasty answer. You don't need it. You're not going to lose any sleep over not knowing it. If you want to know it, you can talk to me after class. So just remember, during the D block, value of N goes down by 1. So I don't care which way you do it. Oh, by the way, you don't have to worry about this if you're using the diagonal rule, because the diagonal rule has that anomaly built into it. Because if we go back and look at our diagonal rule, notice it's got that built in. So it goes 4s2, 3d10, 5s2, 4d10. So that anomaly is already built into the diagonal rule. But if you're using the periodic table, you just have to remember that. Okay, so I really don't care which way you do it, whichever method that works for you. Okay, so let's just take a second just to make sure that we're good at this. Why don't you do, let's do calcium, let's do chromium, and let's do copper 2. You can use either method. Either method. I'll pause the video. Okay, so for those of you students watching online, you probably did chromium, and after I wrote that down, I said, oh man, chromium's an anomaly. We're going to do it in a minute. It's one of the anomalous ones. So I changed it to arsenic. So if you did chromium, you're a student watching online, go back and change your work real quick, and then pause the video and then try it again. Okay, so calcium has how many electrons? 20 electrons. So I'm a periodic table kind of person. That's my preference. But if you like the diagonal rule, that's great. You can use it too. All right, so here we go. 1s2, 2s2, 2p6, 3s2, then what? 3p6, then what? 4s2. All right, let's do arsenic. How many electrons does arsenic have? 33 electrons. Are we starting to notice a pattern here? Starting to feel like a broken record a little bit. That's what I'm hoping you're starting to feel like. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now we're going into the D block, right? So that means it's 3d10. And now we come out of the D block, 1, 2, 3, 4p3. Do we agree? And now let's do copper 2. Copper 2 has gained electrons or lost electrons? It's Cu plus 2 or Cu minus 2? It's 2 plus, right? So that means it's gained electrons or lost electrons? Lost, right? So we're going to treat it like it's gallium or cobalt. Which one are we going to treat it like? We're going to treat it like it's cobalt, right? So we're going to, if we're using the periodic table, we're going to count off until we get to element number 27, which is cobalt. All right, it's got 27 electrons. Now, if you're using a diagonal rule, you just count till you get to 27, right? But if you're using the periodic table for a cation or an anion, you need to factor in, has it gained or has it lost electrons, and then subtract that from where you're counting to on the periodic table, right? Because if you count to copper, Number 29, that would get you copper, the metal, not copper 2, the ions. We need to count till cobalt. So here we go. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. Cobalt gets us 1, 2, 3, 4, 5, 6, 7. Do we agree? Do we agree? So the only thing to worry about with ions, if you're using the periodic table, is if you've added electrons, you got to count further on the periodic table, right? You got to count less on the periodic table if it's a cation. Now, are you noticing some severe redundancy here? Do you feel like you're writing the same stuff over and over and over again? Right? You're writing, all of these have this part in common. Right? All of them have that in common. So we can actually abbreviate this. We can abbreviate our electron configurations severely. And so the way you do that is called a noble gas electron configuration. Noble gas shortcut. So it's a shortcut. Okay, so let's do that one. This one was calcium, this one was arsenic, this one was Cu2+. Let's do calcium using the shortcuts. If we look at calcium, we go up a row and all the way to the end. Argon gets us to here, right? Argon is 18. That gets us to here. So that completely fills all the rows above it. So if we just write argon in brackets, now all I'm responsible for are the leftovers in my particular row. So it'd be argon 4s2. Does everyone see how we did that? So you're using the noble gas at the end of the row above it to get you to the end of your row, so that all your leftovers, all you're responsible for writing are the leftovers in your particular row. So if we're doing arsenic, what element will we put in the brackets there? It'd be argon as well, right? Argon gets us to here, so now all we have to do are the leftovers. So the 4s2, 3d10, 4p3. And then if we're doing copper 2, if we're using the periodic table, we're pretending it's cobalt, right? So again, we use argon, that gets us to 3p6. And then we're left over with 4s2, 3d7. That make sense? So now if I give you something like, you know, palladium, you won't give me the nastiest, dirtiest look you've ever conceived, right? So why don't you do palladium, number 46, using the noble gas shortcut? Now, if you're using the diagonal rule, you would need to count off where your noble gas ends on the diagonal rule, and then you would start where the noble gas ends. Okay, so just make sure you do that. If you are using the noble gas shortcut on the diagonal rule, you would say to yourself, okay, argon gets me to 18, so I got to count off to 18, and then start where argon ends. You don't start back at 1s2. Palladium. Now, if I said write the full electron configuration for palladium, you'd probably not be too happy with me, right? Because that's a long list. But using noble gas shortcut, it's not too bad. What element goes in brackets? Krypton. And then all I'm responsible for are my leftovers. Right, so there's palladium. So what's N for palladium? 1, 2, 3, 4, 5. All right, so 5s2, 4d, 1, 2, 3, 4, 5. Oops, I lost count. 1, 2, 3, 4, 5, 6, 7, 8. Do we agree? That's a whole lot shorter than starting at 1s2, right? Now again, if you're using a diagonal rule, you would start at 1s2, count off to where krypton ends, and then you would start at 5s2. Okay? Don't write krypton and then start writing 1s2, 2s2, 2s2. That doesn't work. Right? You would calculate on your diagonal rule where krypton ends, and then you would start where it left off. Okay, so that is the one downside to using the diagonal rule for the noble gas shortcuts. All right, let's talk about orbital diagrams. Orbital diagrams. They represent electron configs visually. I'm pretty sure I have one in my PowerPoint, so I don't have to draw it out on the board. Let's see. No, I don't. Doggone it. Where is it? It must be in the other classes. Hold on, let me pause the recording. All right, found what I was looking for. So, orbital diagrams just represent electron configurations using a visual method. So I will give you the boxes. You need to fill them. Okay. Now, we have one little rule that we have to follow. Electrons are represented by up arrows and down arrows. Right? So the reason why one of them's pointing up and one of them's pointing down is because they're opposite spin. So this one might be spinning clockwise, this one's spinning counterclockwise. Okay? So one arrow is pointing up, one arrow is pointing down, but it's half arrows. And we have to use Hund's rule, which says basically give each box its own electron until you are forced to share. So I will give you these boxes. You just have to be able to fill them properly. Right, so let's do some together. And normally I'm going to give you way more boxes than you'll possibly need so that I can test if you know where to stop. All right, so let's do magnesium. So that's 12 electrons. All right, magnesium's got 12 electrons. So here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, that works out nice and neat. What if we had one like, let's do something like phosphorus. Phosphorus would be 15 electrons. So that gets me to 12, 13, 14, 15. That would be the correct answer for phosphorus. Okay? Hund's rule, in a nutshell, says it's of lower energy if you have degenerate orbitals that are split up. Okay? In other words, we don't want to have 2 in the 3p box right here. We want to have them all split up. Just like if I rent a van and I'm like, all right, guys, we're going on a field trip. We're going to go wherever. All right, first person gets on, they get their own seat. They sprawl out. Right? Second person gets on, they sprawl out. Third person gets on, they sprawl out. Fourth person gets on, they sprawl out. Now when person number 5 gets on, they say, all right, somebody scoot over, we got to share. Right? So everybody's going to take up their own seats until I force you to have to share. Okay? So an orbital diagram is just a visual representation. And by the way, this is where magnesium stopped. This is where phosphorus stopped. This matches the electron configuration exactly, right? Because magnesium's electron configuration is 1s2, 2s2, 2p6, 3s2, right? 1s2, 2s2, 2p6, 3s2. It matches it exactly. And then for phosphorus, it would be 1s2, 2s2, 2p6, 3s2, 3p3. Right? 1, 2, 3. So this matches the electron configuration exactly. It's a visual representation of an electron configuration. So I'll give you the boxes. You just need to know how to populate them. Okay? Now for the last couple of minutes, we have to talk about some anomalies. Remember when we did chromium a minute ago, I was like, ooh, scratch that. Chromium's an anomaly. Let's talk about their anomalies. There are 4 anomalies in the periodic table that you're responsible for. We won't get to valence bond theory today, but that's okay. We can do it next time. So we've got some anomalies in the periodic table that we have to take into consideration. So there are 4 elements. Let me get rid of this for a second. So I've got a blank screen here. 4 elements with anomalous electron configs. And here are your 4. So on your periodic table, put a little star next to these guys. Chromium, which is element number 24. 24. And then go directly underneath it, molybdenum, which is number 42. And then copper metal, not copper ion. Okay, copper metal, number 29. And silver, number 47. Now, just so you know, this technically applies to tungsten and seborgium and gold and rhodium, but I will never make you do ones that require you to go through the F block. Okay, tungsten number 74, seborgium 106, gold 79, and rhodium 111. Those all are in the same boat, but those 4 require you to go through the F block, and I'm not going to make you write electron configurations involving the F block. Okay, so just know these 4. So let's talk about, if you understand one, you'll understand the other. And if you understand this one, you'll understand this one. So let's talk about chromium. Right? So its electron configuration, let's do the shorthand version, would be what? Argon, what? 4s2, then what? 3d4. Now that's what you expect. Right? So in terms of an orbital diagram, 4s, 3d. That's what you expect. What you observe is argon, 4s1, 3d5. That's what you observe. Anyone want to guess why you would observe this? Anyone want to guess why one electron gets stolen from the S and dumped over here? So yeah, exactly. And the quantum mechanical explanation is beyond the scope of this course. But in terms of quantum mechanical stability, it's more stable to have the D block fully filled halfway. So in other words, if you're 1 away, this 1 electron actually gets yanked from the S block and into the D block. So that the D block, every single one of them has 1 electron. Okay? Now, this only happens if you're 1 away. If you're 2 away, doesn't affect you. So it's like those students emailing me at the end of the semester, I'm only 1 point away. Actually, you're 1 percentage point away, which is different, but beside the point, right? If you're 1 away, that's where this happens. Okay, so that's why it does not affect vanadium, right? Vanadium's 2 away, it won't affect vanadium. So it affects chromium and molybdenum the same way, because if you look correct, chromium, molybdenum's directly below it. It's 1 away. The only difference between chromium and molybdenum is this will be 5 and 4 here. Okay. Now let's look at copper, because if you understand copper, you'll understand silver. So here's copper. Cu is 29 electrons. So what you expect would be argon, then what? 4s2, 3d9, right? That's what you expect, which corresponds to this. Right? What do you observe? Anyone want to guess? You observe argon 4s, what? 4s1, 3d, 10. Right, that's what you observe. That's a 10, 1, 0. Right, this electron gets stolen because now quantum mechanically it's more stable to have the D block fully filled. But again, it would not affect nickel. Nickel's 2 away. It doesn't affect you if you're 2 away. It's just if you're 1 away. And because it affects copper, silver is directly below it for the same reason. The only difference between copper and silver is that this will be 5s and 4d. And just so you know, technically it would affect gold and rhodium too, but those two require you to go through the F block, which I'm not going to make you do. Okay? Just so you know. Those are the 4 anomalies. So on your periodic table, put little stars next to those 4 elements on their boxes, so you remember that there's this anomaly that occurs where 1 electron gets stolen from the S block and into the D block, either to make it halfway filled completely or fully filled completely. Okay? And like I said, in terms of electron configurations, whether you use the periodic table or the diagonal rule makes no difference to me. So whichever you are more comfortable with and leads you to the correct answer, I have 0 preference on which method you use. Okay? I prefer the periodic table. That's my personal preference. But if you like the diagonal rule, then by all means, please use it. Okay? Because that's why I teach it, because maybe you like that better. So electron configurations, we got through all that today. We won't get through valence bond theory today. We'll do that next time. That's okay. So I hope you have a good day, and I'll see you